For the methods for our experiment, we use power lab, preamp, and the nerve chamber. We use a lot of wires. You guys know how it goes.
To give background to our experiment, now we'll explain the physiological mechanisms at the neuromuscular junction. Threshold is the minimum voltage that the membrane potential needs to reach before an action potential can fire. Cap is a compound action potential that is the summation of different individual action potentials which recruits different subtypes of nerve fibers. The subtypes vary in sensitivity to stimuli because they have different myelination and diameter. More myelination and bigger the diameter, the more sensitive the nerve fiber is to a stimulus. The most sensitive subtype is the A alpha, then A beta, then A gamma, then A delta. Neuromuscular junction, also known as the end plate, is where the presynaptic alpha motor neuron terminal meets the muscle fiber cell. Packed in the presynaptic vesicles are acetylcholines. In the membrane of the presynaptic terminal, PQ-type calcium channels are embedded. As the cell depolarizes, the PQ type will activate and let calcium through. A alpha axon carries an action potential. Depolarization hits the presynaptic terminal. When depolarization spreads in the terminal, the PQ channels will activate, which will increase the calcium permeability. This will cause the vesicles with acetylcholine to exocytose to the synaptic cleft and diffuse across the synaptic cleft. The acetylcholine molecules will bind to the nicotinic receptors on the muscle fiber cell. 2 acetylcholine molecules per receptor will bind. Nicotinic receptor is a mixed cation channel, but because the resting membrane potential is further away from the equilibrium potential for sodium and close to the potassium equilibrium potential, the driving force for sodium is high. The high driving force for sodium will cause sodium ions to go through the receptor and cause depolarization. The end plate potential is not an action potential. This is a graded potential based on the amount of acetylcholine diffusion, activation of receptors, and how much sodium comes in. The voltage-gated sodium channels that are next to the end plate potential will activate when the end plate potential is bigger than threshold. The end plate potential will spread passively to the parts of the membrane that are close to the end plate potential where the voltage-gated sodium channels are. This will cause a muscle action potential. The muscle action potential will spread in both directions. In our experiment, we'll be measuring cap and map recruitment and synaptic delay. Synaptic delay is the time it takes between presynaptic depolarization and postsynaptic depolarization. The delay comes from the individual steps that happen in the synapse: release of neurotransmitters, diffusion of acetylcholine, and nicotinic cholinergic activation.
For the experiment, we did not expect any changes to occur with atropine because atropine blocks muscarinic receptors, specifically on smooth muscle. In the parasympathetic system, atropine binds to cholinergic muscarinic receptors and competes with acetylcholine for the receptor. With atropine, acetylcholine can no longer bind to the receptor and initiate a GQ-coupled pathway, leading to contraction. However, in our experiment, we saw a decreased excitability with atropine. Our max map amplitude decreased and our synaptic delay increased. Atropine caused a reduction in duration of the end plate potential by modifying the acetylcholine receptor reaction, which causes a shortening of the ion channel and lowering its conductance. Instead of competitively inhibiting acetylcholine, which happens in the parasympathetic nervous system, the acetylcholine can non-competitively shortens the receptor occupation and lowers the affinity constant. Less duration of the receptor acetylcholine interaction means less ion conductance because less sodium is coming to increase depolarization. Less sodium means decreased end plate potential, which would lead to decreased MAP as well. For dantrolene, we expected no change in synaptic delay or MAP amplitude. This was expected because dantrolene acts as a ryanodine receptor antagonist in the postsynaptic muscle cell and inhibits calcium release from the sarcoplasmic reticulum. Because this would affect the contraction and is downstream of what we are recording, we predict that this would not affect our MAP amplitude or synaptic delay. We observed a decreased MAP amplitude and an increased synaptic delay, which indicates an overall decreased excitability with dantrolene. The decrease in excitability can be due to dantrolene inhibiting intracellular calcium release and decreased neurotransmitter release. There is evidence that dantrolene can inhibit intracellular calcium release from calcium storage sites in the presynaptic neuron, such as the mitochondrion, endoplasmic reticulum, and microtubules. For adenosine, we expected a decrease in excitability, causing a decrease in max MAP amplitude and increase in synaptic delay. We expected this because adenosine acts on adenosine 1 receptors on the presynaptic neuron. Adenosine 1 receptors is a muscarinic receptor that results in GI-coupled signal cascade. This ultimately results in a potassium channel activation, which leads to an outward potassium flow. This will hyperpolarize the cell. This was observed in our data, and the max MAP amplitude decreased and the synaptic delay increased. This makes sense because the receptor activation causes a GI-coupled signal transduction, which causes a decrease in cyclic AMP, which also causes potassium channels to open. This led to hyperpolarization of the presynaptic neuron and decreased excitability. This experiment was interesting because the NMJ is susceptible to have a decrease or increase in excitability depending on the treatments done to the muscle. All the treatments had an effect that was unexpected except for adenosine. This stresses the importance of understanding all the mechanisms behind the NMJ function in order to correctly prescribe treatments that will prove to increase the quality of life for people.